Here comes our examples. So what I'm going to try to give to you is some type of suggested setup for, well, basically the problems and the examples that you're going to see. A lot of the other resources that I saw out there, they kind of allude to this, but they don't list them out like I do. I'm a list type of guy, and again, I'm really hoping it helps you. But in our directed proof, we've already discussed the concept. We're going to assume the antecedent, which is the P of a given statement, is true, and then we're going to use our understandings of the different logic, actually some math and other items like that to end up proving that our consequence or our Q is also true. So now I want you to almost pause this so you can read this over. I'm not going to go this step by step because honestly, I'm going to show you an example of it. But you really need to have this overall setup here. And I highlighted 3 and 4 in this, which is frankly the spots that cause the most consternation. It is the most work. I'll leave it at that. So let me go over example number 1 with you. In example number 1, I'm asked to give a direct proof of the theorem if n is odd and an integer, p, then n squared is odd. Now, by the way, this is already in the form of p and q. Now, also, by the way, I put the words, or I shouldn't say words, but the variables p and q in there, to try to help you out. But notice there is an if and a then that's already there, so we know it's in the form of our P implies Q. Again, we have to be careful about that in some of our overall toolkits that we're going to have. So different proofs that we're going to have in our toolkit, I should say. But this one's already done for us. And again, I was the one that labeled the P and Q that's in there. So our number 1 is done. The theorem is already in the form of P and Q. You're going to have an example of where that wording is close. There's something like it, but then you might have to add something to get it into the P and Q, and you'll see that in a minute. So our next part is assume that n is odd. Okay, we've done that. Number 3 is that, hey, we know it's an odd integer, and we're trying to prove that n squared is odd. So what does odd mean? And we've talked about this before in other mathematical definitions. We know that n is going to be 2k plus 1 for any integer of k. So again, that's coming right from the definitions that we know of, or mathematical definitions that we know of. So it's something worth listing down, but also notice it gives us an available equation to use in order to frankly do number 4. Number 4 is where things get interesting, and we talk about it in great depth here, either next page or the page after. Is now what the heck do I do? I'm trying to prove that n squared is odd, or my Q portion of this implication, or theorem, or whatever the heck you want to call it, is true. So what I'm trying to do is basically break this down so that I can get to my next part of, wait a minute, this form, which has got some magic happening here, that form looks pretty close to our 2k plus 1, proving that, hey, wait a minute, that's actually odd. So that's what's happening in number 4. There's manipulations being done with very simple math of foiling and then looks like combining some things and then going from there on how to do that. But again, my goal was to get something that looks very close to 2k plus 1 because again, we know that part is odd. So in number 5, here's the trick of the whole thing is using substitution. We got the equation to look pretty close to what we have already for an odd. So what I'm going to do is use substitution from the original equation. Now I have 2r plus 1 where r equals that whole bunch that was already in there. And we have that the k is an integer. That's proving that no matter the equation, it has a part of it in there that definitely says, hey, this is going to make it odd no matter what. And that's really what part 6 is saying, is that we've proved that n is an odd integer and n squared is an odd integer, and then it's our finishing stamp on the whole thing. But notice, there's that substitution. What we have here, we get that equation to look something similar to their mathematical definition of our odd. And then, hey, it's a part of that equation. It's part of it here. That looks very similar to this. We've got it. Here is example number 2. In example number 2, notice the question or the statement given is very different. So again, I'm using the same steps as I had above, so you may want to have that with you there. Prove that the sum of two rational numbers is rational. So notice there's not an if and a then on this one, but I can change it into that, and that's with step number 1. If R and S are two rational numbers, which is our Q, which means that they are rational numbers, okay, remember our different symbols that we have here, then the sum of those rational equals another Q or another rational number. So notice I'm putting in some symbols in there, here and there. I have my if, which is going to be my my P portion, and then we have our then, which obviously after that is equal to our Q variable in our overall proposition. So P implies Q. Now that we've changed that, it's the same question, just a little bit set up differently when it comes to our P and Q implication. Now we're going to go ahead and assume that R and S are rational numbers. That's step number 2. In step number 3, we have to make sure that we understand what rational numbers are, because again, that's going to give us some mathematical formulas that we're going to be able to manipulate to do that tricky substitution that we need to do on here in a little bit. So I literally just copied and pasted what the definition of a rational number is. And notice we have a couple of things here. B does not equal 0, and that G equals A divided by B. By the way, when we're looking and doing some things online to find what a definition is, the variable naming may get kind of convoluted and a pain in the neck. Like, I think they used R, I think they used P and Q and stuff like that. That's going to make things complicated because we are already using P and Q. So I changed up the variables. I didn't change up the equation. All I did was change up the variables, and that's about it. So here's number 3, is using the definition of a real number above, there it is right there, then there must be an integer A, B, and also T and U for each part of R and S fractions such that they were this. Now, why am I even talking about that? Because remember, there's 2 parts of the equation that we had, which was R, that 2 rational numbers, and notice I named them R and S. So they didn't appear from the heavens. I set them up. They're both R and S are rational numbers, so they have to be broken down into, well, what rational numbers is an A divided by a B, where B is not equal to 0. That's exactly what I'm saying here. So again, I really didn't invent too much here. All I did was use the definition of what a rational number is to break it down into further parts, and again, denoting that B does not equal 0. Now again, what am I after? Where am I at and where am I getting after? I'm trying to show that the overall result of those 2 numbers being added together is also going to be another rational. So I am giving another form of an equation that I need to start to get to so I can do my substitution. So the nice part is it's actually not all that hard. I just add R plus S, do all of my shenanigans there with adding things together, and then I do my substitution. So when I do my substitution using V and W, V is equal to the top portion of that equation that we had just here, and W is the last part, and B times U cannot equal 0. I've put it back into a form of another rational saying, hey, this has got to be a rational because, hey, here it is in that form again. Yes, I got to do some substitution, but there's the form. So that's why it's really important to do that substitution. Really honestly, 3 and 4 are getting things in order. 4 is the one that's trying to manipulate it to get back into the form that we want. In this case, it happened to be a rational number, which is a division. Again, I keep pointing to the original definition here. And that's where we get to our 5, do the substitution, say, hey, wait a minute. Even with the substitution, I'm showing you that form of a rational again, and bam, there it is, our conclusion. Thus, the sum of 2 rational numbers is rational. QED with our stamp on it at the end there. But again, notice a lot more, not a lot of extra work, but there is some pulling and tugging on this to get this one to be proven. Very similar problem for our next one, and that's this time the sum of 2 even integers is even, or are even. I think it should be is even, but whatever. Same overall setup. Notice the overall statement that we're given is not really set up in our P implies Q form, so we're going to go ahead and do that. If 2 even numbers, or integers, even integers, A and B, and notice that Z is for integers, are summed together, that's their P portion, then the sum of Z or really of our, keep saying z here, that's our sum of our integers is even, and that's our q part of our definition. Again, the same setup with the same instructions that we had before. Part 2, assume a and b are integer numbers. Part 3 is go ahead and do our definition. Well, an integer, if it's an even integer, it's going to be a equals 2 times k. For some k is an element within an integer, or that k is some type of integer. And then b equals 2 times m. Now notice that just use two variables, but the form is still the same, where again m is also an element within an integer, or it is an integer. Then we do combine our two equations. Again, we're trying to, if it's even, we want to try to get it back to our form of 2 times something. So we're going to multiply this out first, and then we're going to have to push it back together, basically saying, wait a minute, I've already got the 2, and then this part right here is a multiplication, so that's what we're going to do. We're going to do our substitution where r is k plus m, just in those parentheses, and the r has to be an integer. And here we've gone ahead and figured that form out, and again we can say the sum of two integers, or therefore the sum of two integers is even, and there's our stamp on that.